Okay, just remind you that if you're the beta recording, I upload it after that from Twitch, and I stream to Twitch, and it doesn't compress nearly as aggressively as the compression on Zoom. So you can see me with both, but the video quality in Twitch is better. And then I upload it to D12 from Twitch. Okay. Homework, quick questions? Yeah. You're given a polygon, but you're given a polygon which is not necessarily convex, and you want to create a convex hull of this polygon. But it's important that you're given a polygon that is legit, simple. That is, it's a polygon that is non-simple is, for example, this. Polygon with hole is not simple. Same as this, not simple. But what you're getting is a legit polygon. Simple, no holes. So somehow you want to massage this polygon to get it. Video would be nice. Windows sometimes. So in terms of my personal favorite algorithms that we are going to discuss today is really one of the highlights of really cool, brilliant ideas that how did they think about it, but we are going to speak a bit more general linear programming and then dive more into the really fast methods that had a lot of other applications elsewhere. So we are talking about an intersection of half planes. We'll have a lot and lot of half planes today. Yes, Mir? What happened to it? That's because I just said that it's good quality and obvious. So we are going to have a lot of half planes today. What is a half plane? Here is a line Li, and age I is everything on one side of this line, or possibly the other side of this line. But there are two half planes. And what happened when I have a few half planes that are put together, then you also have a cost function that tries to push you in some direction without limitation of generality. We'll say usually it will prefer to go downward, that is to minimize a y value. It will be written less. But there is some direction, and because of the cats that we had yesterday, that we had in the previous meeting, the more I'll go into this direction, the better my cost function is. If it worked a bit, then I should continue in the same direction, which will push me maybe from some point into an edge of the feasible region that I'll keep following until I'll hit a vertex. In 3D it will maybe push me into a, now in 3D my feasible region is a convex body. Maybe gradient descent will push me until I hit a face. I'll keep following the face until I'll hit an edge, and then I'll keep following this edge until I hit a local minimum, which because of convexity is also a global minimum. And that would be a time to stop and say that's the optimum. Yeah, that's a bit unpleasant. Let's hope that it will go down. Do I have anything in OBS to close? Video, not really. Hopefully. Anything I can close. Sometimes maybe seems to make things worse. We'll We'll give it a second if it will not stop. We have to decrease the not to kill zoom, so that's not what I meant to do. Okay, give it a moment or two, and if it will not help, solution to linear programming. We said linear. Yeah, we're going to it. So it's enough to look for a vertex that is a solution of the linear programming. Convexity is behind everything here. Right, it will be a vertex if it exists. In general, you have intersection of half planes, half spaces. It could be that there is no solution at all. That was a case of one half plane, another half plane. So far, they have a nice intersection over here, another one over here, and now they have no intersection. Every two have intersection, but there is no point that belongs to the whole three. It could be unbounded. Let's say I'm trying to maximize these directions, or it could be not unique. Two vertices that give me the same value, let's say, of the lowermost point. Simplex algorithm. Fantastic algorithm, extremely influential. Was developed and was used supposedly to help transportation problems in the German side. The needs of airplane cargos. There's many applications, either as direct application for communication, networking, network flow, really numerous applications of the simplex algorithm for linear programming, both as giving application for integer, giving approximation to integer linear programming, or linear programming itself, usually not in 2 dimensions, but in higher dimensions. But the algorithm is a version of steepest descent. I'll pick a direction, try to follow it, keep a direction and try to follow it while staying inside the convex region, for example. And we have to use this algorithm, especially in this algorithm, in higher dimension rather than building the feasible region directly. Feasible region, as we said, all the points that satisfies all the conditions, all the vitamins that we have, but ignoring issues of cost. And why do we have to, how many vertices can we generate in the feasible region in 2D? How many vertices can I have if I have the half planes H1, H2, dot, 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 Hn? Only Fn half planes. How many edges can I generate? Not too hard. Here is one that belongs to one half plane. Another one belongs to another half plane. Another one belongs to H3. Another one belongs to H4. Here is H5. That is another constraint that actually doesn't contribute any edges to the intersection. So in half plane, you can construct, and you will in homework 2, you will construct the feasible region directly in 2 dimensions, and it still has linear complexity. That's good. It will still take n log n. In higher dimension, we don't really want to construct a feasible region, all the possible solution in d dimensions. Why? Because there might be, and it's not very hard to generate, cases where the number of vertices is exponential in d half. So in 3 dimensions, it's still linear, convex hull of, but if you have n faces, we'll think about it, we'll talk about Euler formula that actually implies that if you have n faces, then you also have n vertices, roughly, and n edges, but it really goes exponentially bad in higher dimensions. It is still poor quality of the video because I see that the computer, the fan finally stopped. So maybe there is a sign that it gave us up. Is the quality of the video any better? So now the audio also dropped, so they can't hear me. Okay. We can communicate, we can have both. They know about multiprocessing. Okay, just to connect the diet problems to what's happening in higher dimensions, we solved the diet problem when we had oranges and bananas, X and Y. We have now types of foods, D types of food, D is the dimension. I would be the banana, I equal 1 will be the banana, I equal 2 will be the oranges, 3 will be avocados, and so on and so forth. X sub j is the amount of food j that we need to consume daily, 1 to 3 all the way up to D, D4 dimension. You can think about it as a vector, of course, in the D dimension, as a point. Now it's becoming a point. I have a lot of types of vitamins that I want to satisfy. Aij, how many units of vitamin I there is in vitamin J. Yeah. How many units of vitamin J there is in a food of type I. Again, think about vitamin I as a vector of these values, these lists. Bj, another constant that's given to us, is what is the minimum daily dose of vitamins that we need from vitamin of type I for I equal 1 to n. It cannot make any sense unless you went through the example in 2 dimensions. Otherwise, I'm going way too fast. Bi is how many the daily minimum amount of units of vitamin I that you need to get, which now means that this big sigma, which in vector sums would be, take AI, the constants that you need of how many units of vitamin 1 you have in banana, how many units of the same vitamin in orange, how many units in vitamin of the same vitamin in avocados, and so on. Takes this vector of constant times the vector x, that's what we are trying to find, x1, x2, dot, 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 xd, how many units of each food am I going to eat, how many oranges, how many bananas, how many avocados, takes a dot product that must be at least bi, you must get enough of each one of the vitamins, and your cost function, again, repeat to what we discussed on Tuesday, is not only how much a banana and avocado cost, but how much avocado, other types of food cost each one, C1, C2, all the way up to CD, another constant. So what I'm trying to minimize is C, the constant vector C, times X. X is what I'm looking for, but for this I'll just take X equals 0, or X equals minus infinity, if there is such a thing. I don't have to pay much, but I'm looking for actually X only inside the feasible region. Only among X's that you're getting enough many of all the vitamins. I'm really scamming through this slide because it's just a generalization word by word of what we did for avocados and oranges. For bananas and oranges. And oh, by the way, if you like matrix multiplication, then all these vectors, A1, A2, AD, I can put in this big matrix A, and then they become matrix A times X should be larger or equal than a vector B. A vector B, if you're familiar with linear algebra of matrix multiplication, and I'm trying to minimize, just as before, C dot product X. C transpose dot product X. Okay. Dancing gave the first algorithm following World War II. Great algorithm in practice, even in very large inputs, very large data. However, in some very rare cases, it can be exponential. You can give it an input that it runs exponentially time. Question of either algorithms that always runs in polynomial time was the 80s. There is actually interior point algorithm that does something like this. There is a separating hyperplane, another method that actually we recently used for applications of graphical models and pandemic in kind of a cool way, recent publications. Going down in the dimensions, for small dimension, is there a hope for a linear time algorithm? Nimrod Megiddo gave one in '84. It's linear time, but it's a great example that constants are really should deserve more respect in this course. It's linear time, supposedly fast, with a constant of 2 to the dimension square. It's interesting theoretical, not very practical, not even in lower dimension. And this is a deterministic algorithm. Always doesn't toss any coins. Algorithmic complexity independent of D, probably not very likely because of curse of dimensionality. If you want, there is a difference between pseudo-polynomial versus polynomial. Probably not. But let's look at this sort of Megiddo, this really, really complicated algorithm that is deterministic, and instead I'll give you a very simple randomized algorithm that also gets to linear time, but with much, much, much smaller constants. So for n log n time linear programming, again, in 2 dimension, I'll leave you various details to figure out in the homework, but let's say that here is one subset of half planes that I already computed. The intersection, and just for the drawing, I'll assume that they are all pointing upward. The point 0 and infinity, way, way up at the top of the building, this point is inside all these half planes. None of them contains the other half plane. And in general, every half plane is in one of the two unless it's vertical line. So all of them contain this high point. Let's assume that I already computed their there it's called the upper envelope, the feasible region that they define, everything above them, and there is, let's say, assume that there is n half of them, which I already computed. And here are another set of similar half planes that also points upward. Okay, that I also computed, and there is n half of these guys. Now I can merge them to compute the intersection of everything here, and it will only take linear time. Think about it, line sweep will do the trick for you. Which will mean that now I can do, similar to what we did in the convex hull divide and conquer algorithm, I can do something very similar for intersection of half planes. Okay, and I'll let you figure out some details, but it's essentially line sweep. What is more surprising a bit is that you can even do it in linear time if the slope are sorted. Yes, sir. Sorry? Upper envelope are all the points that are above all the lines. That is, the boundary is this region. If I fall from infinity, I look at all the points that I might hit. That's the upper envelope. But you'll have the details in the homework, but n log n definitely you can do. Or you can solve convex hull. How is this related to convex hull? Because lines and points are dual. We'll talk about it later in the course, waiting for us later in the course. But I want linear time algorithm, or at least expected linear time algorithm, and much faster. So to get a much faster algorithm, I will first discuss the one-dimensional problem. So here is one-dimensional linear programming. I think that the computer tries to get the Dropbox to access something that, because I'm not a super user, I don't have access. And my hope is looking okay on Twitch, at least. Does Twitch? Okay. Okay, then I will hope that it's fine. Okay, I'm given now 2n constraints or half planes, but all my half planes are just in 1D. Namely, they are just points on the lines. All the alpha i's and the beta i's are only points of the line, and my linear programming is given this two-dimensional point, find the minimum value of x such that x is larger than every alpha I, and at the same time x is smaller than every beta I, beta j. Help? Randomized algorithm, deterministic algorithm, whatever you want. Help? I'm looking for the minimum value of x that is larger than all the alpha I and smaller than all the beta j's. Or figure out that there is no such x, of course, it's another option. Sorting will definitely work. Yes, and go ahead. Sorting is n log n, but it gives us all the intuition. So if we'll sort them, finish the sentence. But which of the alpha i's do I care for? Actually? Only one alpha I is really matters. So that's exactly what you said, right? That's what you meant. I look at all the alpha i's. I can sort them, but essentially all I care for is the largest alpha I And from all the beta j's, I cared for the smallest beta j. And now what is a feasible region? Everything here in between, if it exists. It could be that actually the smallest beta j is to the left, smaller than the largest alpha I. So, and in this case, I'll figure out that the feasible solution is empty. Good with everybody? So it's just finding the maximum and the minimum. So the sorting is nice to understand what's going on, but it's not necessary. You can find maximum without in linear time. Okay. So all the x's such that x is between the maximum of the alpha i's, maximum of the small point, and the minimum of the large point. Here is exactly the same question, but it looks more confusing. And there is more letters involved. So, and let's start to get used to this notation. I'm solving one-dimensional linear programming on a line L, However, this line lives somewhere on the plane, oriented somehow. And in addition to this line, I'm giving a set of half planes, H1, H2, all the way up to Hm. And the point that I am trying to find must be on this line. So it's one-dimensional problem. I'm not looking for a point that floats in 2D. It's a 1D problem, only on the line, but this point that I'm after should be inside all the half planes. So I want to convince you that it's exactly the same problem, just with more notation. So just to get used to the notation, big intersection sign from I goes from 1 to M. You know what is sigma, the summation. Big intersection, it just means H1 intersected with H2, intersected with H3, intersected with all the way up to Hn, the geometric region of all the intersection of the half planes. In the vitamins diet saying it was all the diets that satisfies vitamin A, vitamin B, vitamin C, and so on. Okay, so let's see how we are doing it. We said some half planes contain this point. Some half planes contain the opposite point at the bottom of the building, minus infinity. I will meditate on the ones that contain the uppermost point, and we'll get rid of the one that contains the lowermost point, for the time being. Let Li be the line that bounds Hi. We'll keep this notation later. Li is just the line that is a boundary, the border of the half plane Hi. And for every Li here, compute the intersection point with this input line that I gave you. Remember, I'm looking for solution only on L itself. So I'll compute the first intersection point, second one, third one, in this case, always L. And what am I looking for? I'm looking for on a point of L that lies on this line, but is above. If my cost function is to minimize, then I'm looking for a point that is above each one of these intersection points. That is, it's anywhere on the ray that is emerging from the maximum of the values. One slide ago, this line was horizontal. I just oriented it a bit. And I mentioned now I'm constrained as half planes instead of just being larger than, but it's exactly the same thing. Okay, as far as this line cares, it's on the x-axis, and it doesn't care. So among all these half planes, find the higher one, the rightmost one, the one with the maximum x or maximum y, doesn't matter. And now it's time to remember the other ones. They are defining similar points, and among these points, I'll find the lowermost one. Again, just minimum operation, linear time as well. Now, think about it. From the maximum point, I'm shooting a ray upward from the lowermost point, I'm shooting a ray all the way downward, both in L. Where is my feasible region? Between these 2 points. What is my optimum value for any optimization function? It's either this point or this point, depending if you want to minimize or maximize. Okay? Everything is in linear time. And once again, it's important, if this maximum point is somewhere here below the maximum, this ray doesn't have any intersection, and then the feasible region is empty. Your linear programming doesn't have a solution. But here are all the feasible points, but it can be empty as well if I change my constraints a bit, depending on where it's at. Okay, let's talk about n-square algorithm to solve linear programming in 2 dimensions. And now it will be an incremental algorithm. We had an n log n time algorithm that I hand waved with, and now I'm downgrading into an n-square slower algorithm to solve the same problem. So it's incremental algorithm. What is incremental? I'm going to add 1 half plane at a time. I'm going to add 1 half planes at a time. And I'll start when I have 1 intersection points. That is intersection of 2 half planes, one optimization point. And now I'm going to add 1 half plane at a time. H2, H3, H4 will be added. And at each moment, I'm not going to keep the whole feasible region. It's a bit hopeless if I'll try to maintain the exact each and every vertex of the feasible region. All I care for is keep the optimal solution, just 1 vertex, the ones that give you the optimal value. And when you're adding a half plane, maybe you'll be lucky. And if you're lucky, you don't need to change the optimal solution. If you're unlucky, then we will see that we just need to solve a 1-dimensional linear programming problem. Notations. Age I is a ith half plane. We talked about it. Age I is just a I half planes. And to remind everybody, we are looking for the minimum y. I'll assume without generality, without any limitation. Let's get started. For visualization, let's say that our cost function C is 1, 0. Is 1, 0, sorry, is 0, 1. 0, 1, meaning the x value in the cost I don't care at all. For the y, I'm trying to make y as small as possible. Everything that I'm saying will work with any cost function, any linear cost function, but visualization-wise, it will help me. So I'm looking for the smallest y, which would be which will satisfy so the minimum cost function of 0x plus 1 times y, such that the point xy belongs to age 1 intersection age 2 intersection age 3 ... age n. That's a problem that we are trying to solve all the time. Right? Each half plane is one of the vitamins, and I'm looking for a point that the diet that is cost me the least. X goes for free for some reason. I'm only paying for y, and I'm trying to satisfy all my vitamins constraints. Somehow only oranges are expensive, but bananas are very cheap, so I ignored. That's the story. Notations. Age I, that's the I half planes of constraints. Li always is a line that bounds age I. New notation. Ci is the intersection of age 1 intersection with age 2 intersection with all the way up to age I. Remind you, we are looking at incremental algorithm. We are going to add constraints one after the other. So at each moment, I'll add one more constraint to this set of constraints. I'm defining Ci. It doesn't mean that I'm going to compute it. I'm not going to compute Ci. I'll just know that it exists at the intersection of the whole thing. Intersection, that's a feasible region. Of course, Ci might be empty. Vi is what I definitely going to compute, to maintain and calculate at each operation. Vi is the optimal solution to the first, I should have highlighted it, I constraint. That is the lowest point of Ci. I'll play a bit on the whiteboard with this example. First on the slides. Here is V2. C2 is this whole infinite wedge that goes over here, the intersection of these two guys. And I'm about to add age 3. What's the next? What is C3 right now? That's the half plane that I added. C3 is this whole region. And V3 is just the lowermost vertex at this region. Let's play with a few more examples. Here's age 1, age 2. Where is V2? That's V2. I'll add a half plane. You'll tell me where is V3. Age 3. Still V2. I don't change it. But still V2. It's still the lowermost point. I mean, there is age 3, but this is V2, but also V3. Age 4. Still, it still didn't change. This is also V4, the very same point. Now, C4 has changed at each interaction, or at least in this half plane it changed, this half plane it didn't. Age 5, where is V5? Good, everybody? This is V5. Age 6 still exists. Actually, I didn't mean it, but it's still, yeah. Always in the ferry side. Age 2, where is age 2? Oh, sorry. Where is V6? Here. But and now let's add blue. Blue, blue, blue. Age 7, where is V7? No V7. No feasible solution. Okay, so everybody good with the notations? Okay, this is both the theorem and the algorithm at the same time. Here's the theorem. V6 have higher value of y. That's correct. I'm looking for the lowermost point, but since age 6 pointing downward, then the feasible region is just this tiny little sliver over here. So I'm at the ith step of the algorithm. I know what is vi minus 1. Vi minus 1 is a solution for the first I minus 1 constraint. And now I'm looking at age I. Age I is suddenly in the game. And now the theorem, that is also the algorithm, says if vi minus 1, the previous best solution that you had until this moment, if it doesn't violate the ith solution, the next vitamin that you just introduce, if it doesn't violate it, like in the case of H3, if it's not broken, don't fix it. But whatever was the optimum that you had earlier, if now you do, it doesn't violate the new constraint, then it's still the optimum. Right? So if vi minus 1, the previous optimum solution that you had, is still in hi, then vi equals to vi minus 1. Just change the name if you wish. But it's still the same point. If vi minus 1 is not in hi, then I cannot use the previous solution. That was the case when I moved from 3 to 4. I had to change my plus 1. So it looks like I need to solve, if I cannot use the previous solution, then why did I do all this gymnastic so far? I still have a two-dimensional linear programming right now. But there is an aha moment. I still have a linear programming problem, but it's not two-dimensional linear programming. It is one-dimensional linear programming. The new solution must be, and there are figures coming, the new solution must be not just on hi, like, because it needs to be in all the hj's, all the half planes. But it's not only on hi, it's on the border of hi. Okay, look for a solution, but only on the boundary of the new half planes. So use the one-dimensional linear programming that we saw a few slides ago for this problem. Which means that if I couldn't find a solution on Li itself, then there is no solution at all. Even though I was looking for a solution only on this line, if on the line I didn't find a solution, then the feasible linear programming is empty and no reason to check hi plus 1, hi minus 1. But, for 30 cents per day, you cannot get a healthy diet, maybe. Okay. So let's prove it. First part, this one is trivial, right? Clearly, if this was a previous optimal solution, your new constraint doesn't violate it, it agrees with the new constraint, then it's still the optimal solution. How long does it take to check it? Well, solution would be, I can represent a half plane in many ways. If the half plane is represented as ax plus by is larger than c, right? Then just take the new solution, vi, put it here and here, and see if it satisfies. Maybe I'll make it ai and bi and ci. Okay, for the ith constraint. Okay, part 2 is a surprising part. So remember, there is ci, that is the intersection of age 1, intersection age 2, intersection. It's not what I compute, but it still exists. Here is age I, the brown thing, everything above this line. And here is ci minus 1, some intersection of half planes. The lowermost point of the previous half planes, before I added the brown one, is vi minus 1. Just to make sure that everybody is cool with the notation. That's the optimum for everything excluding hi. And now I'm about to add hi. Had hi be all the points above this line, then obviously vi minus 1 would have done. Otherwise, here is hi, and it violates vi minus 1. I need to find a new solution. Now, let's assume by contradiction that the new solution, vi, is not on this line. Where is it? it is by definition inside age I and inside all the previous half-planes, the intersection of all the previous half-planes, inside this brown thing. But it's not on Li. So here is Vi, not on the boundary itself. Okay, understand that if Vi is here, it contradicts my solution. Remember, it's not a global optimum. I'm just talking about the first I. There are more half-planes to come in the future. I don't know about them yet. But here's Vi. Not on the boundary of age I, not on Li. Vi minus 1, Vi, which one is lower or which one has better cost function, what it is? Of course, Vi minus 1, because it solves fewer constraints, satisfies fewer constraints. Less restriction about Vi minus 1. Geographically, it's just lower by definition. Vi less desired, more expensive. What does the cost function is linear, meaning that if this point is better than this point, that as I'm moving from Vi, which is in Hi, into Vi minus 1, which is not in Hi, as I'm moving along this segment, my cost function changes linearly, becoming better and better, lower and lower. Graphically, it's obvious, but true for any linear function. So here is a point not in on, here is a point which is inside Hi, a point not in Hi. As I'm walking down this segment, at some point I must exit from Hi. I must exit through Hi, through the only border of Hi, which is Li itself, right? And this point Q is better, lower, better cost function than Vi. Contradiction. Contradiction to what? To the assumptions that Vi is not on the line, Li. So it's pretty cool, because it is not true if I just throw Hi randomly out there for any constraint. It's because Hi did not satisfy the previous optimal solution, I can deduce something about what happened when I'm adding it all together. I need all the conditions of the sentence, right? So that was the cat theorem that we mentioned about the linear, the putting a rope around the equator. Okay. Here, let's say, here is the algorithm, but it's pretty much the theorem. Sorry. Ci that I will compute is just the intersection of the first half planes. I'll compute it, and I'll compute what is Vi, which is the optimal solution when just the first two half planes are in the game. And now I'm going to add the half planes one by one. And for each one of the half plane, Hi, if the previous optimal solution, Vi minus 1, belongs to it, does not violate it, then Vi is just the previous optimal solution, and it takes me a constant time to check it. Else, Vi is, let's say, theorem, Vi must be on the line that bounds Hi. So, called the one-dimensional linear programming, where the line L that we mentioned is just the boundary of Hi. Let me go back one slide. My one-dimensional linear programming would say this line is fixed. That's a line that I'm looking for my solution on, and all the other half planes, age 1, 2, 3, all the way to age I minus 1, that's the other half plane that I'm giving. But I'm only looking for a solution along this line. So I'm applying the 1D linear programming. Cool. So if Vi must be on the line, so-called the 1D linear programming, notice the parameters. The line is Li, the boundary of Hi, and the half planes are everything up to H1, H2, all the way up to the current half plane Hi. If the one-dimensional linear program does not find a solution on Li, then there is no solution at all, and stop. No point of adding other Li. Otherwise, set Vi to be the solution that you got from the 1D linear programming. Okay, and this is our algorithm. What is running time? Worst case running time. N squared. It's possible that at every step I need to call the 1D linear programming. Calling the 1D linear programming is expensive. It's linear time, but now I'm doing it for every half length, just to show you that it could be. The 1D linear programming, I don't have any control. It's linear in I. So here is age 1 and age 2, and every new half planes, age 3, age 4, age 5, age 6, each one violates everything that I've found so far. So I need to call the 1D linear programming for every new age half plane, every new half plane that I'll call. So altogether, the running time is 1 plus 2 plus 3 plus 4 plus dot 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 plus n, which makes it theta of n squared. A constant times n squared, no more, no less. But everybody familiar with this sum, right? It's n times n plus 1 half. Just algebraic, arithmetic, the arithmetic summation. It's n squared. Okay, so it could run in n squared, which is inferior to the n log n algorithm that I mentioned earlier. So far it looks pretty pathetic. So far, everything good? Okay. From now it starts to be really cool ideas and newer, much newer ideas. So now I am not going to take the half planes, the order that they were given to me. Instead, I'm going to insert the half planes, but before, I think that I deleted the slides, they shouldn't. Create a random permutation of the half planes. You have the same input. I don't change the input, I just change the order of the half planes. So I start with an array, age 1, age 2, age 3, all the way up to age n. And I want to create a random permutation of these half planes. I'm going to make the day of some students now. What am I going to do? I'm going to pick a random number. I'm going to pick a random number between 1 and n. Let's say that I picked age 17. Now I want in my new permutation to have age 17 at the end of the array. Not at the beginning of the array, I want it to be at the end of the array. So I'm going to switch age 17 with age 1. Decide that age 17 is here, whatever age n moved here. And now I'm going to do the same process again, but now the index that I'm now going to pick is not between 1 and n, but it's between 1 and n minus 1. Pick an index between 1 and n minus 1, put it at the end, and so on. So you never pick the same number twice. Each one of the half planes have the same chance to be at the last one, the same chance to be at the second from last. Each permutation has exactly the same probability to be picked. But if you have the numbers 1, 2, 3, then you have 1/6 chance that it will appear as 1, 2, 3, 1/6 chance that it will appear as 1, 3, 2, 2, 1, 3, 2, 3, 1, and 3, 1, 2, 3, 2, 1. Right? You have 6 permutations. Each one of them has exactly the same probability that you'll pick it. does it mean that the algorithm will not take n squared time in the worst case? Well, depending on your karma, if you have a really bad karma in your previous incarnation, you did some terrible things, no, you'll hit the permutation that gives you the n squared no matter what. But it's not very likely. If you think about my example with the n squared running time, what happened? I picked these two guys, and then I inserted them from this permutation was age 1, age 2, all the way up to age n in this order. Right? What would happen if I pick age n and age 1 to start with, and then insert the other half planes? Then this will be V2, this point, and age whatever it is, this age I will say, I'm cool with this solution. It doesn't violate me. Nor this one, nor this one, nor this one. So the running time will be linear. So that's the best case. N squared will be the worst case. What is more likely? Well, I want to convince you that it's much more likely that we are getting into the that the linear case is much more likely. And that's using an idea that made its entrance somewhere at the beginning of the 2000s and really got a huge impact. It's called backward analysis. It says, let's assume that I already inserted somehow I half planes. Here is the intersection of the I half planes. Well, think about all these I half planes. Here are all my half planes, each one is a circle, and two of them are somehow special. Right? Look at this lowermost vertex at the intersection. There is one such vertex, the lowermost one, and I'll assume that there is no three half planes that go through this half plane. Actually, if I have three, it runs even faster. So let me just assume every vertex is determined by only 2 points. There are no three lines that intersect in 1 point. So here is a vertex that is a minimum, and there are two special half planes that determine the minimum. But how do I know VI? It is the lowermost point of these two very special half planes. Good? It's really important. Exactly two of them, no matter how many half planes do I have. In general, the optimum is determined only by these two. So I'll mark them as red both. One of them would be H prime. Intentionally don't call it H I. H prime, one is H double prime. What's so special about them? I don't care. But it's only two of them with this special rule that they determine the optimum right now. And now, let's assume that I'm taking any permutation of this particular half plane, only of this particular half plane, only of these I. Only of these I really change my optimum solution. No, doesn't matter at which order I'm entering these half planes that you see in the picture, the optimum solution will be the same, meaning that the two red guys will be the same. Now tell me how likely it is that these half planes appeared in my random permutation as the last one. It appears somewhere in the permutation. If now I have 1, 2, 3, 4, 5, 6, 7 balls, and here I have 7 balls, and one of them is special, then the chance that it appears as the last one is exactly the chance that it appears as one before the last, or the chance that it appears one before, or at the beginning. It's completely symmetric. That was for H prime. H double prime, same deal exactly. Same probability that it appears anywhere along this path. Why is this called backward analysis? Because I can think about it in reverse now. I already entered all these I half planes. I decided about their identity. I entered all of them, and now I pick one of them at random and remove it. What's my chance that if every half plane has the same probabilities that I'll remove, what's my probability that I'll remove either this guy or this guy, the one that determines the optimum? There is 1 over I, 1 over 7 chance that I'll delete this guy. There is 1 over 7, 1 over I chance that I'll delete this guy. That is, the probability that I deleted one of the two ones that determine the optimum is 2 over I. If you're throwing all these half planes, all these 7 half planes, and asking in random permutation, asking what is the chance that the last ball that you are looking at is red, the probability here will be there are 2 red balls out of 7. There is 2 over 7 chance that my last ball is red. Meaning that if my last ball is not red, what does it mean? That when I'm adding the 7th half planes, it is neither this one or this one, but these ones are already inside. That's really brilliant. These ones are already inside. The chances are much higher. Which means that in the I step, I don't have to call it. If it's already inside, then if I call this half planes, I don't need to do any work. If I call this half planes, I don't need to do any work. So the probability that at the I step of the algorithm, Vi minus 1 violate Hi, that is, that Vi minus 1 is not Vi, is only 2 over I. If I was in one dimension and asking, hey, you have n points on the line, y1, y2, y1, y2, y3, yn are all points. And I'm asking you, I am removing all of them, and now I'm putting them back at a random permutation. What's the probability that the last one that I'm adding is the largest one, the one that determines the optimum? What the probability is that the last one is the largest one? It's 1 over n. Because this particular point, the maximum, has the same probability at a random permutation to appear the first one or the second or the third or the last one. So the probability that the I step I need to call the one-dimensional linear programming is only 2 over I. If I were in 3 dimensions, then the optimum determines by 3 half planes, so it would be 3 over I. 1 dimension, 1 over I, 2 over I's, means that the probability that I don't have to call this, the linear programming is I minus 2 over I. Sure, it's probability, but it's very, very basic. I'm not doing anything else. So what if I repeat it a million times, but of course, reset my random variables at each time? At the I step, let's say, at the end step, what is the chance that I'm calling the linear programming? I'll call the linear programming only in 1 over n, 2 over n, sorry, of the cases. So what's the expected work that I'm doing at the I step? I'm spending a constant. What you see here is a constant, no matter what. I'll spend this constant just to check that Vi is in the right place, of the Hi. I cannot avoid it. But now, what is the chance that I need to spend C times I? C times I I'm spending if I'm calling the 1D linear programming that happens only if the Vi minus 1 and Vi are different. The last half planes violate the new half planes violate the previous one. So I'm spending a linear time, linear work in I, but only in 2 over I of the cases, if it's random. And notice the randomness is only on the order. I don't mess up with the input. The input is as vicious as you designed for me. But I just change the order of the insertions, and by random order, the expected work that I'll do at the I step is I work if you need to call the 1DLP times the probability that you need to call the 1DLP, which is 2 over I, making it C times I divided by I times 2, making it a constant. So the expected work of each step is a constant. It's a bit hand-wavy because I don't want to assume that you know random variables. With random variables, it's completely trivial. Without random variable, you still get the whole thing. The larger I is, if I need to call the 1DLP, the larger I is, I need to spend more work, but the chances that it happens is going smaller and smaller. As I increases, the work for 1DLP goes higher, but the chance that I need to go it is lower, so the product stays the same. So every step is, well, expected work for every step is just a constant. Sum up n times constant, you're getting an expected linear time of order n. And with a bit more probability, you can even prove that it's with very small standard deviation. There is great chance that it's closer to n. It's very unlikely that you're closer to the n square. So there was a reason that people were struggling from the 80s until 2004-5 with this extremely complicated algorithm of Nimrod-Megiddo, instead of seeing this 5 lines algorithm that I just described to you, that gives practically the very same result. Okay, so I think that it's very cool. And just to make sure, the probability analysis is not, you can generate a bad set of constraints, but there is, yeah, sorry, I didn't see the false claim. Yeah, I'm not claiming that there is good inputs and bad inputs. I don't, you design the input, you're trying to get my algorithm to run as slow as possible. All I control is at which order I insert the half planes. So the probability analysis is valid for any input. Just you decide about the order. What are you doing in 3D linear programming? Linear programming, you have avocados. You like avocados. You want a diet of oranges, bananas, and avocados, so you are solving 3D linear programming, and you have a lot of these questions in the homework. I'll give you a problem, and I ask you to use linear programming to solve it, but there is only 3 or 2 variables that you need to solve. So 3D linear programming, what's the algorithm? I'm adding, now I have half spaces, not half planes, but the constraint, the boundary Li that I had earlier was a line earlier. Now it's a plane, and the half space is everything on one side of this plane. All the z, such as z, is positive. It's an example. So what are you doing? You insert the half spaces one by one. If you are maintaining Vi as before, the optimal of everything that you have seen so far, you start, of course, with 3 half planes instead of 2, yeah, because you need to start somewhere, so start with 3 half planes instead of 2. But now you're starting from I equal 4, you have V3. If Vi does not violate age I, not broken, don't fix it. Then the previous solution still works, just as in the 2D case. Just call it Vi instead of calling it Vi minus 1. Completely analogous, except now your check is not AX plus BY, but does AX plus BY plus CZ is larger or equal than B for XYZ, just to see if it's inside a half plane or not. So now, if you don't need to fix it, it's fine. Nothing to do. What are you doing if Vi violates AGI? vi minus 1 violates Hi. It's not in the right half plane. What would be the analogous of the Thiem's theorem? What can I say about my solution now? Let's go back. What's my solution tells me now? What the theorem tells me now? Edge I, now we have space, violates Vi minus 1. But my new solution must lie on, help? My new solution is not on the line Li, but is on the plane Hi. Okay, so how do I solve this problem? Use a 2D linear programming, because now you have a 2D problem of solving linear programming on a plane instead of looking for the 1D linear programming. Now you are calling the 2D linear programming. So you went one dimension lower, which in turns might call the 1D linear programming as it wants. But recursively, you're just calling the 1D linear programming. So let's go back to this slide. In this case, the 2D linear programming that we just established, where your solution is on Li, and your constraints are H1, the first constraint intersection with this plane. A bit harder to compute, but you're rotating everything, so this is, say, the XY plane, and it's really not hard to calculate it. And it's easy to implement, and it actually runs extremely fast. For lower dimension, it's quite surprising. There is really nothing here, and it's really clever idea, and you guess what's the next step. 4D linear programming. You're running it, maybe you need to call recursively the 3D, which might call the 2D, and so on. Okay, so, but it's becoming more and more interesting. It's still linear. The running time is still the expected running time. And of course, I'm cheating here. In any fixed dimension, the running time is linear in the number of constraints. But D needs to be small, because there is a constant that depends on the dimension. And this dependency is still unpleasant. It's still going almost exponential in the dimension. But why is this? Why does it work? Why is this justified? Because if in the higher dimensions, the worst case of bad permutations could be actually called to run in n cube in 3 dimension, in n to the 4th in 4th dimension, and so on, while the expected chance, well, now the chance of violation is 3 over I instead of 2 over I. Big deal. Still a constant. Okay. Yeah, that will be already the application. Just to give you the complete spiel. The actual running time is, if you're not doing anything clever, is the factorial, unpleasant, just for this algorithm itself, times that if you're not doing any special tricks. So these small, still very reasonable. Okay, what I'm planning to do next is to leave a bit computational geometry for a meeting or two and talk about what can we do with integer linear programming, which I'm not describing exactly, but if I insist that my solution has to be integers, then suddenly there is a whole area of problems, not necessarily geometric, including geometric, but not only, that I can solve, including NP-hard problems. And why this is a good thing is that because you have libraries that solve integer linear programming, and they are very accessible. As students, you can use Cplex, you can use other libraries that solve integer linear programming and are optimized to death. So you have your very personal strange problem, but once you phrased it, once you made it into an integer linear programming, and you can use this library that is very general, good chance that you'll live long enough to see the solutions within a few minutes. which is unlikely if you try to run through all the exponentially many solutions for this problem directly. And you're sure that it's the optimum solution. It's not heuristic. If it stops, it will report the global optimum solution at the end. So let's spend a meeting or so onto this avenue. Thanks, everybody.